Hey guys, this is Matt. Welcome back to part 2 of the RSA algorithm, where we're going to actually look at encryption and decryption of a string that Bob is sending to Alice using her public key to encrypt it and her private key to decrypt it. So this is part of the cryptography on simple cipher series, and where we look at the mathematics on these simple ciphers. This is, as we said last video, it's a bit more complicated than the normal algorithms we've been using. Most of them have been just add 13, take away, whatever, but this one has a lot more math. So we're looking at how to encrypt the data. We're going to use C equals M to the power of E mod N. And then to decrypt it, we need M equals C to the power of D mod N. And then some information bringing over from part 1 is we found the public key was 7, 187, and the private key was 23, 187. Now, if you have no idea how we got to that point, I would advise you go back and watch the previous video. If you have any more questions, I will post the same video, same references that I have in the first video on details in this one, and by Professor Don Patterson. There's one by a software engineer in Canada that does a great job. I mean, all these sites are very, very good, and this will give you a good educational resource to be able to push yourself in better understanding of the RSA algorithm. So Bob needs to send a message. So his message will be set as a string, which we're going to call it the orange message of cryptography. Most people just put, that I've seen so far with these examples, have just said, oh, we're going to put hi and say that it is have 8 being H and 9 being I. Well, that doesn't seem extremely realistic for me. So as usual, we're going to put it into a char list, because all a string is an array of chars. So we're going to convert it to ASCII, which is what is the more realistic way that this will actually happen. And we're going to look at how do we encrypt this. So you're welcome to go through double check, but this is correct. So, and we've got our ASCII table out so we can look. Encrypting the message. Well, how do we do this? Because we don't want to send this in clear text. And Bob has already contacted Alice. He's got the public key from her, so we're going to use that, and we're going to need it. So we've got, what all do we need to encrypt it? Public key, the original string number list, and the algorithm. So just starting off, we've got from left to right, we've got our cipher, text, the unencrypted message. E would be the coprime, mod N would be the multiplied N. So we're going to take M, we're going to just start off from left to right, because as I mentioned in the previous video, I was unable to get the data type for the decryption process to work because the number was too large. You will see that in this video. And M to the power of E, I was able to get the encryption, but I did all this by hand so that you can see it and work it out with me. So this is this number here. And this is a large number, not large compared to the decryption process, but it is fairly large. So you can use a calculator for this, but we saw how this one here was mod N. Well, you can say that it's this mod something else, but if you don't know how to calculate mod, it does you no good. So how do we calculate A mod B? Well, we divide the two numbers, so A divided by B. Then we take B and multiply it by our quotient, so a mod b. Now, you see this int here. This means that we're not taking the entire decimal value at the end. We're not taking and converting it to a fraction and no, we're taking just the base number. So it's going to be b times another int. Then we have a mod b, so for our final value is a minus our answer from here. So b times this, a divided by b. So that is how we get it. Now, don't just take my word for it. Let's actually work this out. So a mod b, we've got a, which is this monstrosity of a number, mod 187. So a and then b. So this was our m to the power of e, and this is n. So now we divide it, round down, we get a slightly smaller number, which is great. So then from here, we take it, b times a divided by b, and we keep that int, and we get this. Now, ironically, which this generally does not happen, our final value was equal to the original number list 0. This generally is not the case. However, just in this case, it was. So I'm going to give you just a moment to go through and calculate position 1. And keep in mind, in programming, we use 0, 1, 2, 3, not 1, 2, 3. That doesn't work. So 0, 1. So please calculate it for 114, and I'll give you just a moment. All right, so this value is 126. We went through the same process, and the final answer was 126. So from there, we once again go to this, mod n e7 187, and we need this. So this is the full original number string list for you to be able to look at. You can go through each calculation if you would like. I'll give you just another moment to be able to calculate through those. And your full answer will be this. Whoops. Psych. There you go. This one. So we've got 67, 126, 77, 73, 74, 155, 137, and on. So you can go through this for each of these numbers, and well, these ints, and you'll be able to come up with these ints. So encrypted message. Here is our encrypted number list. Now this will turn into this. Now in one of the links, it discusses a buffer. Now depending on the length of your of the actual encryption depends on if there needs to be a buffer. If you're just sending just the message almost as is, then you're going to have it like this. However, most of the time, if not 99.99%, except for within tutorials, you're going to have a lot of additional math to actually meet the buffer standards, whether it is adding a bunch of random ints to the end, filling it in with garbage, but so that this, instead of just getting this message here, you've got a much longer value so that it's much more difficult to actually collect. Most of these are 2,000 plus. I mean, you can have that. You've got an AES 256. You've got all sorts of different ending values and types that you're going to be able to go through to actually see how long these numbers actually get, and so it's a lot tougher to actually calculate this. And so we've got our encrypted message. Well, now what? Well, decrypting the message, we do need our private key and we need the encrypted message. Now, given the situation we're in and given the time constraint we've got, we are looking at I don't exactly have time to go through trial and error and brute force to find out each individual character and int within this. So I'm just going to make it easy and break it apart so we don't have to guess, well, is it 15 or 155? Is it 137 or is it 13? And we don't have to guess how many there are. So from here, we're going to need all of this information to be able to decrypt it, because Alice wants to see what Bob sent. So we use m equals c to the power of d mod n. This is the decryption algorithm. And I would highly advise use a calculator and use the mod button. These are very, very long numbers. And this is where I ran into some issues with C++, not having a data type to be able to actually hold these decrypted, especially within C to the power of D. Is just looking at it, we've got our 67 is our 0.0 and 23. So C is 67 to the power of 23 is a very long number. So if you want to see these broken apart, this is once again not entirely advised, but for those of you that want to continue, we will push on. And so this is just our C to the power of D. Then A mod B, we are going through and actually calculating this out. Due to the lack of room that I actually had, I had to kind of put this in scientific notation due to that. So I would once again highly advise you just take it, put a parentheses around 67 over 23, and then put mod 187. That way you don't have to worry about, because although a lot of the time that these are zeros, sometimes like with this example, I did have to condense it down. So not all the values are seen. So you will have to divide it if you continue on with calculating it out. And you're going to get this, another monstrosity of a number. So now we have B times A mod B, which would give us an even more just ridiculously long numbers. And then we have our final result, which is 67. Although these do look the same, keep in mind I did have to shrink this due to the lack of space on the screen. So your final answer is 67. If you want to go back and double check, just type open parentheses 67 to the power, which is your caret, 23, close parentheses, mod 187, and you will come up with 67. So to be able to continue to decrypt it, you're going to need our private key, M, your algorithm, and you're going to need the list, and our first, which is 0, position is 67 for our decrypted number list. I will give you a moment to decrypt position 1, and we will continue. Okay, so that's 114, and once again we continue on. We will need all of this and this. Now, going through and decrypting it, originally these slides and this presentation was in a different order. So when I got to this point, this is just kind of a funny story, I had forgotten what I had originally put. So it was one of those that I was just as surprised when I saw the end as when I chose it in the beginning. So you can go through, calculate these out. This is your final, the decrypted number list, and you can go through and check that right now. Okay, so now that you've had some time to check that, we're going to, of course, convert these back to ASCII letters or characters so that we can actually see what the message is. So we have our decrypted number list, and then we break it out. Each one corresponds to a number on the ASCII table. If you don't know what an ASCII table is by now, I would advise you go back and watch my previous video on ASCII tutorial. But we can clearly see that the entire message was clearly delivered in the end to Alice. So this is the end of the video. Thank you very much for watching. I really appreciate it, and I really hope this has been beneficial to you. I really want to thank you for your time. If you do have any questions, please let me know within the comments, or shoot me a message, shoot me an email. If you want to see more ciphers broken, or if you're needing help breaking a cipher, if you're needing help figuring out the math behind it, let me know. I'm more than happy to help, and I'll be happy to help any way that I can. Going through and looking at Shor's algorithm, which I believe we mentioned in the very first video, that's going to be added to my quantum series, where we discuss quantum computation, quantum cryptography, and quantum encryption. And the quantum computers right now, although we're still within the NISQ era, they have been able to break the RSA algorithm in just a very, very, very short time. So although the quantum computers are not commercialized, right now your information is safe using, well, relatively safe using the RSA algorithm. However, things will be changing coming up in the future. But for right now, this is the standard that is used. If you have any more questions, please let me know. And thank you very much for your time. I really do appreciate it. Thank you very much.